Good day and welcome to Big Bad Tech. I'm instructor Jim Pytel. Today's topic of discussion is three-phase AC. Our objective is to examine three-phase AC on an introductory level. Three-phase AC is the biggest thing to hit you little kids. Bigger than guns, bigger than cigarettes. Three-phase AC is how electrical power is generated, transmitted, and used on an industrial scale. People unnecessarily fear three-phase AC circuit analysis because they instinctively assume it's 3 times as hard and takes 3 times as long as single-phase AC circuit analysis, but that's not necessarily the case. Do we happen to know that three-phase AC circuit analysis is essentially identical to single-phase AC circuit analysis, only phase shifted? This is to suggest that all single-phase AC circuit analysis techniques we've learned thus far are still applicable, and most three-phase AC circuit analysis scenarios don't require any special skills. This being said, three-phase AC circuit analysis does take a level of organization and visualization on your part. My advice is to simply pick a direction and stick with it. Go A to B, B to C, then C back to A. As long as you remain consistent and don't switch horses midstream, you'll do just fine. As the name implies, three-phase AC is 3 sinusoidal AC waveforms with the same magnitude and frequency, only sequentially offset from each other by a relative 120 degrees. Let's briefly discuss the advantages of three-phase AC and then take a look at how three-phase AC is generated and used. Three-phase AC power presents numerous advantages over single-phase AC power, only some of which I'll mention here. In my personal opinion, the biggest advantage presented by three-phase AC is the establishment of a rotating magnetic field central to the operation of electrical motors. Large motors essentially cannot run without three-phase AC. Additionally, the rotational direction of three-phase AC motors can be quickly reversed simply by interchanging any 2 phases. DC motors and single-phase AC motors, in contrast, have to resort to some undignified trickery or mechanical contrivances to perform the same tasks, and in doing so, suffer some performance degradation. Three-phase AC motors, because they're guided by a rotating magnetic field formed of 3 voltage phases, rotate smoother and exhibit less cogging, which is jerky, step-like movement. In keeping with this smoothness theme, power electronics devices like rectifiers, which convert incoming AC to DC, exhibit notably pulsed behavior when operated with single-phase AC and require extensive work to clean up the output. However, three-phase AC rectifiers produce notably smoother DC output and necessitate less work to clean up the output. Three-phase AC also presents advantages for power distribution and transmission. It may seem counterintuitive, however, a three-phase AC system composed of 3 smaller, thinner, cheaper, and lighter wires can transmit the same amount of power as a single-phase AC system composed of larger, thicker, more expensive, heavier wire. Given the wires in a three-phase AC system are lighter, the supporting structures needn't be as massive nor as expensive. We'll explore numerous three-phase AC applications in the future. Let's now briefly examine the generation process. Consider the act of generating single-phase AC, where a rotating magnet revolves in close proximity to a stationary winding I'll call L1. Let's say the magnet initiates travel as indicated in the diagram and then rotates in the counterclockwise direction. The starting position of the rotating magnetic north pole would be 0 degrees. Stationary winding L1 is physically located at 90 degrees. In its most simplistic terms, a generator is a stick with a magnet on it. If you rotate the stick with a specific torque and rotational speed inside the stationary windings, rotational mechanical power input is exchanged for electrical power output minus losses via the process of electromagnetic induction. As the North Pole approaches winding L1, induced voltage becomes positive and increases in magnitude. In this scenario, we're assuming positive voltage means plus to minus in the counterclockwise direction. When the North Pole is aligned with L1 at 90 degrees, output voltage achieves a positive peak. As the North Pole recedes from winding L1, induced voltage is still positive, yet decreasing in magnitude. When the rotor reaches 180 degrees, induced voltage crosses 0, going negative. As the South Pole approaches winding L1, induced voltage is negative and increasing in magnitude. In this scenario, we're assuming negative voltage simply means a swap in polarity such that plus to minus is oriented clockwise. When the South Pole is aligned with L1, an occasion in which the North Pole is at 270 degrees, induced voltage achieves a negative peak value. As the south pole recedes from winding L1, induced voltage is still negative, yet decreasing in magnitude. At 360 degrees or 0 degrees, the process repeats itself as induced voltage crosses zero, going positive. Given these observations, induced voltage as a function of angular position obviously demonstrates sinusoidal behavior. Given the rotor rotates at a constant speed, angular position is a function of time, and induced voltage can also be plotted as a function of time. Assuming the rotor completes a full revolution every 20 milliseconds, at 5 milliseconds, output voltage achieves a positive peak. At 10 milliseconds, it crosses zero, going negative, and at 15 milliseconds, output voltage achieves a negative peak, and at 20 milliseconds, it crosses zero, going positive, and the process repeats itself. This should be pretty easy to understand. Let's step this process up a notch. The generation of three-phase AC follows an almost identical course. A three-phase AC generator includes two additional stationary windings, L2 and L3, physically displaced from winding L1 by a relative 120 degrees. Given we located winding L1 in black at 90 degrees, winding L2 in red is physically located at 90 plus 120, or 210 degrees. Winding L3 in blue is physically located at 90 minus 120, or minus 30 degrees, which is the same as positive 330 degrees. You'll note winding L2 and L3 are also physically displaced from one another by 120 degrees, where 210 plus 120 is 330 degrees. Winding L2 and L3 are identical in every respect to winding L1, only their physical position on the stator is different. Let's again assume the rotating magnet initiates travel as indicated in the diagram and starts rotating in the counterclockwise direction. The starting position of the rotating magnetic north pole would be 0 degrees. From the perspective of winding L1 at 90 degrees, absolutely nothing has changed, and we should expect induced voltage to exhibit sinusoidal behavior as previously. This being said, it should be noted that while the rotating magnet travels a complete circle, it also interacts with the physically offset L2 and L3 windings. Consider the following counterclockwise rotation sequence. At 0 degrees, the approaching north pole causes induced voltage across winding L1 to cross zero, going positive. At 30 degrees, winding L2 is aligned with the south pole, and induced voltage across winding L2 achieves a negative maximum. At 60 degrees, the approaching south pole causes induced voltage across winding L3 to cross zero, going negative. At 90 degrees, winding L1 is aligned with the north pole, and induced voltage across winding L1 achieves a positive maximum. At 120 degrees, the approaching north pole causes induced voltage across winding L2 to cross zero, going positive. At 150 degrees, winding L3 is aligned with the south pole, and induced voltage across winding L3 achieves a negative maximum. At 180 degrees, the approaching south pole causes induced voltage across winding L1 to cross zero, going negative. At 210 degrees, winding L2 is aligned with the north pole, and induced voltage across winding L2 achieves a positive maximum. At 240 degrees, the approaching north pole causes induced voltage across winding L3 to cross zero, going positive. At 270 degrees, winding L1 is aligned with the south pole, and induced voltage across winding L1 achieves a negative maximum. At 300 degrees, the approaching south pole causes induced voltage across winding L2 to cross zero, going negative. At 330 degrees, winding L3 is aligned with the north pole, and induced voltage across winding L3 achieves a positive maximum. At 360 degrees, or 0 degrees, the approaching north pole causes induced voltage across winding L1 to cross zero, going positive, and the process again repeats itself. In summary, voltage across winding L1 crosses zero, going positive at 0 degrees. It experiences a positive peak at 90 degrees, crosses zero, going negative at 180 degrees, experiences a negative peak at 270 degrees, and crosses zero, going positive at 360 degrees or 0 degrees, and the process repeats itself. In between these key moments, voltage rises and falls as would a sinusoidal function of angular position. Voltage across windings L2 and L3 exhibits similar behavior, only the peaks, valleys, and zero crossings are shifted. Voltage across winding L2 experiences a negative peak at 30 degrees, crosses zero, going positive at 120 degrees, experiences a positive peak at 210 degrees, crosses zero, going negative at 300 degrees, and at an additional 30 degrees, the process would repeat itself. In between these key moments, voltage would again rise and fall as would a sinusoidal function of angular position. Similarly, voltage across winding L3 crosses zero going negative at 60 degrees, experiences a negative peak at 150 degrees, crosses zero going positive at 240 degrees, experiences a positive peak at 330 degrees, and at an additional 60 degrees, the process would repeat itself. In between these key moments, voltage would rise and fall as would a sinusoidal function of angular position. If we compare and contrast the resultant waveforms, we notice something interesting, yet quite predictable. All waveforms have the same magnitude and the same frequency, only they've been phase shifted with respect to one another. The 120-degree physical displacement of the additional windings in the stator has introduced a 120-degree electrical phase shift. All three waveforms can be plotted on the same graph as a function of either angular position or time. This is admittedly a little busy. However, it should be apparent that each waveform is essentially identical, only it's shifted by 1/3 of a full cycle, or 120 degrees. Let's assume each voltage waveform peaks at 311 degrees and repeats itself every 20 milliseconds. A peak value of 311 volts corresponds to an effective or RMS value of roughly 220 volts. A period of 20 milliseconds corresponds to a frequency of 50 Hz. Given each waveform has the same effective magnitude and frequency, only the degree of phase shift really distinguishes these waveforms from one another. Recall that phase shift is a means of relating one or more quantities with reference to another. In order to calculate phase shift, we need to establish a reference. Let's simply assume L1 in black is our reference waveform. Operating under this assumption, L1 can be expressed far more compactly as a phasor equivalent of 220 volts at an angle of 0 degrees. Given waveform L2's zero crossing going positive appears 120 degrees after our assumed reference waveform, it can be said that L2 in red lags L1 in black by 120 degrees. L2 can be expressed as a phasor equivalent of 220 volts at an angle of negative 120 degrees. While it is true that L3 in blue lags L1 in black by 240 degrees, this is admittedly a little clumsy because phase shift is customarily expressed using positive or negative degrees less than 180 degrees. Given the cyclical nature of sinusoidal AC, lagging by 240 degrees is effectively equivalent to leading by 120 degrees. L3 can therefore most efficiently be expressed as a phasor equivalent of 220 volts at an angle of positive 120 degrees. While the combined plot of voltage as a function of angular position or time for the three waveforms is undoubtedly impressive and sure to confuse your non-technical friends and family, the phasor diagram illustrates the most important points far more efficiently. The phasor diagram clearly illustrates all three waveforms have the same effective magnitude of 220 volts, however, exhibit a relative phase shift of 120 degrees between each other. The phasor diagram additionally illustrates another important property, far more efficiently than the plot of voltage as a function of time. If we were to imagine the three phasors not as representations of voltage, but rather three identical forces pulling an object in three different directions with equal magnitude, in which direction does the object go? The answer is nowhere. The three equal forces applied in three equally displaced directions effectively balance each other out. A different analogy might be a hiker traveling three different legs of a trail. If the hiker heads 220 meters at 0 degrees, stops, then heads 220 meters at negative 120 degrees, stops, then heads 220 meters at positive 120 degrees, where is the hiker? The answer is right where they started. Again, the three equal vectors applied in three equally displaced directions effectively cancel each other out. Let's examine other properties of three-phase AC, starting with the generator. Three-phase AC generators place the windings comprising the stator in one of two, technically three, relationships, either a Y or a delta configuration. Before we dive into this section, allow me to caution you to pay attention to the terminology I'm employing here, as it can get pretty confusing rather quickly. Not as confusing as Gabriel Garcia Marquez's novel Cien Años de Soledad, in which 27 of the 32 male characters are named either Jose Arcadio or some variation of Aureliano, but confusing nonetheless because of the similar terminology employed. Let's start with the basics, and then I'll come back to fill in the details. First, we can visualize the three windings as three independent sinusoidal AC voltage sources, each with the same magnitude and frequency, however phase shifted from each other by a relative 120 degrees. Let's use our previous system stats, in which every winding had an effective value of 220 volts. A line is something leading from a three-phase AC generator to a three-phase AC load. A load can also be placed in a wire delta configuration, but to keep things simple right now, let's just ignore the load and concentrate on the windings comprising the generator. Again, a line is something leading from the three-phase AC source to a load. In contrast, a phase is the voltage across an individual winding, often idealized as a source. Here's an important fact. Regardless of the configuration employed, the voltage across an individual winding will remain the same. This being said, depending upon the configuration employed, both ends of an individual winding may or may not be accessible. Additionally, there may exist a differential between lines. Allow me to demonstrate. A Wye configuration pools the assumed negative ends of the windings in a conjoined central node I'll call N for neutral. If three lines lead from this configuration and the central N node is accessible via a fourth wire, this is known as a four-wire Wye configuration. Given the negative ends of the three windings are pooled together in the neutral connection, it should be obvious that line 1 with reference to neutral is 220 volts at an angle of 0 degrees. Line 2 with reference to neutral is 220 volts at an angle of negative 120 degrees. And line 3 with reference to neutral is 220 volts at an angle of 120 degrees. For a four-wire Wye configuration, the line to neutral voltage would be the phase voltage for the windings comprising this generator. But wait, that's not all. If we modify our four-wire Wye configuration by making the central neutral node inaccessible, this is known as, big surprise, a three-wire Wye configuration. While there still exists a differential between a given accessible line and the central node is simply not accessible. This being said, there does exist a voltage differential between the lines. Given the degree of phase shift between the phases, they don't peak and valley at the same time, and we might observe a differential between line 1 with reference to line 2, between L2 with reference to line 3, and between L3 with reference to line 1. We'll examine line-to-line differential in a moment. A delta configuration, in contrast, forms a triangular relationship of three windings, where one winding's assumed negative end stands on the head of another winding's assumed positive end in a continuous chain. This is where it's especially helpful to just pick a direction and go with it. L1's negative is hooked to L2's positive. Let's call this node B. L2's negative is hooked to L3's positive. Let's call this node C. And finally, L3's negative is hooked to L1's positive. Let's call this node A. You'll note not only is a central node inaccessible in a three-wire delta, it doesn't even exist. Given there exists no central neutral terminal, it's essentially nonsense to refer to line to neutral voltage, but rather only line to line voltage. Given winding L1 is between node A and B, it can be said the line-to-line differential between A with respect to B is 220 volts at an angle of 0 degrees. Similarly, given winding L2 is between nodes B and C, it can be said the line-to-line differential between B with reference to C is 220 volts at an angle of negative 120 degrees. Finally, given winding L3 is between nodes C and A, it can be said the line-to-line differential between C with respect to A is 220 volts at an angle of 120 degrees. For a three-wire delta configuration of sources, the line-to-line voltage is the phase voltage, which, if you remember correctly, is the voltage across an individual winding. Again, for a three-wire delta configuration of sources, the line-to-line voltage would be the phase voltage. Compare and contrast this observation with our earlier observations regarding the four-wire Wye configuration. For a four-wire Wye configuration, the line-to-neutral voltage is the phase voltage. In contrast, for a three-wire delta configuration, the line-to-line voltage is the phase voltage. By all means, pause the lecture and stare at this diagram until you can appreciate this fact. Wye and delta configurations of sources with the same magnitude are not equivalent. You'll additionally note that our earlier observations regarding the summation of phasor equivalent voltages make these configurations possible. 220 volts at an angle of 0 degrees plus 220 volts at an angle of negative 120 degrees plus 220 volts at an angle of 120 degrees yields 0 volts. No differentials exist within the delta itself because the phase shift between the three phases balances the complete system. Let's examine the 4-wire Wye configuration in greater detail, since it's a great stepping stone to explore line-to-line differentials. Recall our previous observations about the 4-wire Wye configuration. We determined L1 with reference to our pooled neutral connection would be 220 volts at an angle of 0 degrees. Line 2 with reference to neutral would be 220 volts at an angle of negative 120 degrees, and line 3 with reference to neutral would be 220 volts at an angle of 120 degrees. An additional line to neutral voltages for a 4-wire Wye configuration, consider another mind-blowing possibility, that of line-to-line voltages. Fair warning, it is easy to lose oneself in the briar patch into which I am about to toss you. As such, just sit back and enjoy the show. I'll demonstrate how to achieve these same results in less time using less effort, but the process I'm about to employ is especially elucidating regarding the origins of the shortcut I'm about to show you. Before we dive into the heavy math, consider just waveform L1 with reference to neutral, as not a plot of voltage as a function of time, but rather the height of a wave on the ocean in inches, where the zero center is assumed to be average sea level. If LL Cooltech is surfing the peak of the wave and falls off, he'll fall a distance of 311 inches, or roughly 26 feet to the level ocean. If we include waveform L2 on the same plot, we observe something interesting. If L2 also represents the height of another wave on the ocean in inches, LL Cooltech, surfing the peak of wave L1, looks down past the ordinary level of the flat ocean deep into the negative yet rising trough of wave L2. If he wrecks now, he'll not only fall the distance to the level ocean, but past it, into the trough of wave L2. Long story short, there can be an astounding differential between waveforms exhibiting a phase shift between each other, even if those waveforms have the same magnitude and frequency. Now for the heavy math. Let's consider the instantaneous differential exhibited between waveforms L1 and L2 for a handful of points. Expressed using the time domain, L1 of t is 311 volts times the sine of 360 times 50 times t plus 0 degrees, and I2 of t is 311 volts times the sine of 360 times 50 times t minus 120 degrees. Given the period of a 50 Hz waveform is 20 milliseconds, 5 milliseconds in would represent 1/4 of a complete cycle, or 90 degrees. L1 should be peaking at 5 milliseconds. Substituting this time into the time domain expression yields L1 to have an instantaneous value of 311 volts, as we anticipated. L2, however, should be negative, yet rising. Substituting 5 milliseconds into the time domain expression for L2 yields the L2 to have an instantaneous value of negative 156 degrees. The instantaneous differential between L1 and L2 is therefore L1 at 5 milliseconds minus L2 at 5 milliseconds, or 311 volts, minus 156 volts, or 467 volts. Given the substantial instantaneous differential, this would be a very bad time to fall off that wave. Let's consider instantaneous differential at 10 milliseconds. At 10 milliseconds, this represents half of a complete cycle, or 180 degrees for a 50 Hz waveform. L1 should be crossing 0, going negative. Substituting 10 milliseconds into the time domain expression yields L1 to have an instantaneous value of 0 volts, as we anticipated. L2, however, should be positive and rising. Substituting 10 milliseconds into the time domain expression for L2 yields L2 to have an instantaneous value of 269 volts. The instantaneous differential between L1 and L2 is therefore L1 at 10 milliseconds minus L2 at 10 milliseconds, or 0 minus 269 volts, or minus 269 volts. LL Cooltech, surfing wave L1, watches in horror as a looming waveform L2 blocks out the sun. Finally, let's consider instantaneous differential at 15 milliseconds. At 15 milliseconds, this represents 3/4 of a complete cycle, or 270 degrees for a 50 Hz waveform. L1 should be peaking negative. Substituting the time domain expression yields L1 to have an instantaneous value of negative 311 volts, as we anticipated. L2, however, should be positive. Substituting 15 milliseconds to the time domain expression for L2 yields L2 to have an instantaneous value of 156 volts. The instantaneous differential between L1 and L2 is therefore L1 at 15 milliseconds minus L2 at 15 milliseconds, or negative 311 minus 156, or minus 467 volts. If wave L2 fell onto wave L1, it would be a loud and powerful explosion with LL Cool Tech caught in between. If we perform the same instantaneous analysis for more and more times with smaller intervals between the times and plotted these values, you'll note our results form an immediately recognizable shape. Oh my gosh, it's a sine wave, only its magnitude is much larger and it's been phase shifted. The voltage between L1 with respect to L2 appears to peak at roughly 538 volts, and its zero crossing going positive appears to lead L1, our earlier assumed reference, by 30 degrees. The frequency of the line-to-line differential between L1 and L2 appeared to be unaffected, and that the new waveform repeats itself every 20 milliseconds. If you wanted to, you could perform the same time-consuming iterative analysis of instantaneous values for the line-to-line differential between L2 with respect to L3, and again for the line-to-line differential between L3 with respect to L1. Both analyses yield sine waves with the same frequencies, larger magnitude, and degree of phase shift. The line-to-line differential between L2 with respect to L3 in orange also appears to peak at roughly 538 volts. However, its zero crossing going positive appears to lag L1, our earlier assumed reference, by 90 degrees. Similarly, the line-to-line differential between L3 with respect to L1 in yellow also appears to peak at roughly 538 volts. However, its zero crossing going positive appears to lead L1, our earlier assumed reference, by 150 degrees. If the first combined plot of three-phase AC didn't confuse you earlier, this diagram should hopefully do the trick. You'll note a three-phase AC system configured as a four-wire Y in effect delivers not only three line-to-neutral voltage waveforms, but also three bonus round line-to-line voltage waveforms. In summary, our original three line-to-neutral voltage waveforms each peaked at roughly 311 volts, had an effective value of 220 volts, and a frequency of 50 Hz. The only difference between them is the degree of phase shift at 0 degrees, negative 120 degrees, and positive 120 degrees. These new bonus round line-to-line voltage waveforms each peak at roughly 538 volts. They've got an effective value of roughly 380 volts and a frequency of 50 Hz. The only difference between them is the degree of phase shift at 30 degrees, negative 90 degrees, and positive 150 degrees. Remember these values. Each line-to-line voltage has an effective magnitude of 380 volts and is phase shifted at either 30, negative 90, or 150. Note the time-consuming iterative analysis of instantaneous values isn't the only, nor is it the best way to obtain line-to-line differential for three-phase AC systems configured as four-wire Ys. Recall phasor equivalents convey the most pertinent information in the smallest possible package, notably effective or RMS value and phase shift. Expressed as phasor equivalents, L1 is 220 at an angle of 0 degrees, L2 is 220 at an angle of negative 120, and L3 is 220 at an angle of 120. To solve for the line-to-line differential, one simply subtracts the reference phasor from the phasor of interest. To solve for the line-to-line differential from L1 with respect to L2, perform the operation L1 minus L2. Substituting in our given values yields L1 with respect to L2 is 380 volts at an angle of 30 degrees. To solve for the line-to-line differential from L2 with respect to L3, perform the operation L2 minus L3. Substituting our given values yields L2 with respect to L3 is 380 volts at an angle of negative 90 degrees. Finally, to solve for the line-to-line differential from L3 with respect to L1, perform the operation L3 minus L1. Substituting in our given values yields L3 with respect to L1 is 380 volts at an angle of 150 degrees. Oh my gosh! These are the same values we obtained earlier during the time-consuming iterative analysis of instantaneous values. Using phasors, we got the same results in less time. The subtraction operation illustrated in the phasor domain makes it quite clear that the difference between L1 with respect to L2 is 380 volts at an angle of 30 degrees. I like to think of the L1 minus L2 subtraction operation as, if I'm at the head of vector L2, how far and in which direction do I have to walk to get to the head of vector L1? Likewise for the other two operations. If I'm at the head of L3, I need to go 380 volts at an angle of negative 90 degrees to get to the head of L2. Similarly, if I'm at the head of L1, I need to go 380 volts at an angle of 150 degrees to get to the head of L3. Allow me to caution the viewer to remain organized during three-phase AC circuit analysis and construction. You'll know other combination of differential operations exist, notably L2 minus L1, which yields 380 at negative 150, L3 minus L2, which yields 380 at 90, and L1 minus L3, which yields 380 at negative 150. These alternate permutations are all essentially the back azimuth or negation of our first results. While both interpretations are true, woe unto those that try to mix the two interpretations. My advice is to again simply pick a direction and go with it. I typically go L1 to L2, L2 to L3, and then L3 back to L1. You'd think this cautionary note only concerns itself with esoteric math and has little bearing on the real world. However, polarity of voltmeters, ammeters, and power meters must also take this arrangement into account when taking observations of an actual three-phase AC system. Again, assuming we travel L1 to L2, L2 to L3, and L3 to L1, our line-to-line differentials are 380 volts at an angle of 30 degrees, 380 volts at an angle of negative 90 degrees, and 380 volts at an angle of 150 degrees. One can also zero-center these resultant line-to-line differentials such that each emanates from the central origin. If you didn't notice something interesting about the line-to-line voltages before, it should be pretty obvious now. What's the relative phase shift between the line-to-line voltages? The answer is that they're also all displaced from each other by a relative 120 degrees. If we start at L1, L2 at 30 degrees, L3, L1 is 30 plus 120 away at 150 degrees. If we're at L3, L1, L2, L3 is 150 plus 120, or 270 degrees, or negative 90 degrees away. If we're at L2, L3 at negative 90 degrees, L1, L2 is negative 90 plus 120 away, or 30 degrees. These three line-to-line voltage waveforms are also equally displaced by 120 degrees. Keep in mind that the phase angles exhibited in this diagram are all operating under the dubious assumption that L1 is our reference waveform at 0 degrees. This needn't always be the case, and the honor of serving as a system's reference can easily be revoked at any notice. If we're concerned with not the line-to-neutral voltages, but rather the line-to-line voltages, we can simply pick one of our line-to-line voltages and call it the reference. Since L1 with respect to L2 is closest to our origin at 30 degrees, let's just assume that it's the reference. Re-referencing the system to L1, L2 has done absolutely nothing but shift our plane of analysis by 30 degrees. Our original three line-to-neutral voltages still have an effective value of 220 volts, and they still exhibit a relative phase shift of 120 degrees to each other. The only thing that's changed is the absolute phase shift. Using L1, L2 as our reference, L1 is now 220 at negative 30, L2 is 220 at negative 150, and L3 is 220 at 90. Similarly, the three line-to-line voltage waveforms still have an effective value of 380 volts, and they still exhibit a relative phase shift of 120 degrees to each other. The only difference that's changed is the absolute phase shift. Using L1, L2 as our reference, L1, L2 is now 380 at 0 degrees. After all, it is our reference. L2, L3 is 380 at negative 120, and L3, L1 is 380 at 120. Compare and contrast these two phasor domains. One employing L1 as our reference, and the other employing L1, L2 as our reference. There should be an obvious connection between the two. They're just shifted by 30 degrees. Which is the more appropriate frame of reference, the line-to-neutral or the line-to-line voltages? The answer is, it depends. Is the system you're working on using the line-to-neutral voltage, or is your system making use of the line-to-line voltages? Make your job easy. If your system is using the line-to-neutral voltages, by all means reference everything from one of the line-to-neutral voltages. If, however, your system is making use of the line-to-line voltages, by all means reference everything from one of the line-to-line voltages. In summary, use a reference that makes sense. That's the beauty about references. They're flexible, and you can use or not use a given reference as you see fit. If the shortcut offered by phasor math still seems like too much work, here's an even shorter shortcut for the morbidly lazy among you. You'll note the line-to-line voltage magnitudes are approximately 1.73 times higher than the line-to-neutral voltage magnitudes, and the phase shift for the line-to-line voltage has a 30-degree offset from the nearest line-to-neutral voltage. You'll note 1.73 is the square root of 3. This is not a coincidence, but rather an artifact of a trigonometric identity that I totally have no idea how to do. I did know how to do it once, but as soon as I learned it, I forgot it because it's absolutely non-essential to the key takeaway. Again, the magnitude of the line-to-line voltage is square root 3, or approximately 1.73 times higher than the magnitude of the line-to-neutral voltage, and the phase shift includes a 30-degree offset from the nearest line-to-neutral voltage. A simple algebraic manipulation also shows us that the line-to-neutral voltage is the line-to-line voltage magnitude divided by square root 3, and the phase shift includes a 30-degree offset from the nearest line-to-line voltage. Let's try an application of these simple calculations. Feel free to use phasors or the above-mentioned shortcut. Consider a 4-wire Wye configuration consisting of 3 windings, each with a 120-volt differential across it. L1 is assumed to be our reference and has a phase shift of 0 degrees. L2 is phase shifted by negative 120, and L3 is phase shifted by positive 120. First question. What's the line-to-neutral differentials? L1 to N, L2 to N, and L3 to N. Second question. What's the line-to-line differentials? L1 to L2, L2 to L3, and L3 to L1. The line-to-neutral differentials are easy for a 4-wire Wye configuration. Any load placed between L1 and N would experience 120 volts at an angle of 0 degrees. Similarly, any load placed between L2 and N would experience 120 volts at an angle of negative 120 degrees. And finally, any load placed between L3 and N would experience 120 volts at an angle of 120 degrees. The line-to-line differentials necessitate some minor calculations. Using phasors, L1 minus L2 is 208 volts at an angle of 30 degrees. L2 minus L3 is 208 volts at an angle of negative 90 degrees. And L3L1 is 208 volts at an angle of 150 degrees. If we didn't like phasors and wanted to use a shortcut, we could say each line-to-line differential is square root 3, roughly 1.73 times larger, and it's offset by 30 degrees from the nearest line-neutral differential. Using the shortcut, you get the same values. Again, note both the line-to-neutral and the line-to-line differentials each exhibit a relative phase shift of 120 degrees from each other. If we wanted to, we could also reference this whole system with respect to the line-to-line differentials. Assuming we choose L1, L2 as our reference, L1, L2 is 208 at an angle of 0 degrees. L2, L3 is 208 at an angle of negative 120, and L3, L1 is 208 at an angle of positive 120. Given L1, L2 is assumed to be our reference, L1 is 120 at an angle of negative 30 degrees. L2 is 120 at an angle of negative 150 degrees, and L3 is 120 at an angle of 90 degrees. Either phasor diagram is correct as long as the user is aware of which reference is being employed, either one of the line-to-neutrals or one of the line-to-line voltages. Before we move on, allow me to point out an important feature about this system. Note we've in effect created a dual voltage 3-phase AC system. Load elements using the line-to-neutral connections experience the smaller 120-volt line-to-neutral differential, whereas load elements using the line-to-line connections experience the larger 208-volt line-to-line differential. This is pretty cool. We'll explore applications of this feature and details of Wye-configured and Delta-configured loads in later lectures. If we were to place this 4-wire system inside a box, there would still exist a 120-volt differential between any line and the neutral connection. Additionally, there would be a 208-volt line-to-line differential. If, however, we restricted access to the neutral connection, we'd be unaware of any line-to-neutral differential without resorting to invasive inspection. This being said, we'd still see the 208-volt line-to-line differential. If we're outside the box, are we really aware of what's inside the box? Is it, in fact, a Wye configuration making use of 3 120-volt sources, indirectly making it seem like there is a 208-volt line-to-line differential? Or is there a Delta configuration in there, making use of 3 208-volt sources, directly establishing a 208-volt line-to-line differential? Not really. The moral of the story being, as long as the line-to-line differentials are the same, and we stay outside the box and restrict our analysis solely to the loads attached to the lines, We really don't care what's inside the box. I'll come back to correct this gross oversimplification in later lectures on generators. Our immediate attention really needs to be directed towards three-phase AC circuit analysis and how various loads interact with these different voltage levels outside the box. Okay, let's close out this lecture with a couple quick illustrated example problems. Let's say we got three phases, each with a 277 volt differential offset by 120 degrees. Let's say we hook them up in a 4-wire Wye configuration. What's the line to neutral voltages? What's the line to line differentials? By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. In a 4-wire Wye configuration, the line to neutral differential is the phase voltage of each source. L1 is 277 at an angle of 0 degrees, L2 is 277 volts at an angle of negative 120 degrees, and L3 is 277 volts at an angle of 120 degrees. In a 4-wire Wye configuration, the line-to-line differential is square root 3 times the line-to-neutral voltage magnitude and offset from the nearest line to neutral voltage by 30 degrees. L1, L2 is 480 volts at an angle of 30 degrees, L2, L3 is 480 volts at an angle of negative 90 degrees, and L3, L1 is 150 degrees. Note the line-to-line differentials are still offset by a relative 120 degrees. If we wanted to, we could also reference this whole system with respect to the line-to-line differentials. Assuming we chose L1, L2 as our reference, L1, L2 would have a phase shift of 0 degrees, L2, L3 would have a phase shift of negative 120 degrees, and L3, L1 would have a phase shift of positive 120 degrees. Given L1, L2 is assumed to be our reference, L1 would have a phase shift of negative 30 degrees, L2 would have a phase shift of negative 150 degrees, and L3 would have a phase shift of 90 degrees. Either reference is correct as long as the user is aware of which reference is being employed. Now compare and contrast these previous results with the same windings, each with a 277 volt differential across them, when arranged in a delta configuration. In the delta configuration, there is no neutral connection. So talking about line to neutral voltage is like talking about your lab partner showing up to class on time. Absolute nonsense. In this delta configuration, there is no neutral connection. This being said, there is a line-to-line differential. For delta configuration of sources, the line-to-line differential will be the phase voltage for each particular source. Assuming we chose L1 as our reference, the differential from node A to B would be 277 volts at an angle of 0 degrees. The differential from B to C would be 277 volts at an angle of negative 120 degrees, and the differential from C to A would be 277 volts at an angle of 120 degrees. Again, compare and contrast Wye and delta configurations comprised of windings with the same 277 volt differential. They are not the same thing. The Wye configuration of these windings would have a line-to-neutral differential of 277 volts and a line-to-line differential of 480 volts. In contrast, the delta configuration of these windings would have a line-to-line differential of 277 volts. Let's try another illustrated example. Let's say we walk up to a three-phase AC source exhibiting a 575 volt line-to-line differential, where each line-to-line differential voltage has a relative 120 degree offset from each other. What's the line-to-neutral differentials? By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Given we've assumed L1, L2 as our reference at 0 degrees, all our line-to-neutral voltages will exhibit a negative 30 degree phase shift from the nearest line-to-line voltage. Additionally, each line-to-neutral voltage magnitude will be equal to the line-to-line voltage magnitude divided by square root 3. Substituting in our given values yields L1 to be 332 volts at an angle of negative 30 degrees, L2 to be 332 volts at an angle of negative 150 degrees, and L3 to be 332 volts at an angle of positive 90 degrees. If we wanted to, we could again reference this whole system with respect to the line-to-neutral voltage differentials. Assuming we chose L1 as our reference, L1 would be 332 at an angle of 0 degrees, L2 would be 332 volts at an angle of negative 120 degrees, and L3 would be 332 volts at an angle of 120 degrees. With L1 assumed to be the reference, L1, L2 would be 575 volts at an angle of 30 degrees. L2, L3 would be 575 at an angle of negative 90 degrees. and L3, L2 would be 575 at an angle of 150 degrees. Either interpretation is correct as long as the user is aware of which reference is being employed, either one of the line to neutral voltages or one of the line to line voltages. Regardless, there is still a 120 degree phase shift between the line to neutrals and the line to line voltages. Alright, that's about it for today. There is a lot more to discuss regarding how current flows and how voltage appears for loads in various configurations. However, we'll save these specifics for later lectures. In conclusion, this lecture introduced three-phase AC and examined properties of various three-phase AC systems. We discussed the advantages of three-phase AC, examined the generation process, looked at Y and delta configurations of sources, and learned to calculate line to neutral and line-to-line voltages for different types of three-phase AC systems. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.